Today we have a really great speaker, Kai Wang. Kai is really one of the probably the best researchers I know in this field of halide perovskite photovoltaics. A really great young scientist doing a lot of discovery of various kinds of materials and science. So I think you'll enjoy the insights he can provide in this field, and is very knowledgeable about the fundamental physics that occurs in these materials. And I think this field has advanced very rapidly. So in past few years, probably you've seen a dramatic rise in number of publications and also a lot of young people getting involved in this field. So I'm hoping this seminar will encourage and motivate some of the folks who are listening to really come into this field, because there's so much promise and there's so many opportunities in this area. So hopefully Kai's talk will motivate a lot of students and postdocs to start taking interest in this area and pursue this. And before I pass it on to Kai, I again want to acknowledge National Science Foundation for providing the support and providing this opportunity to host students from Germany and allowing us to send US students to Germany. So this has been a really great and fruitful collaboration with University of Kiel. And so we are hoping that the students or postdocs in Germany, if they are interested in this area, they will come to Penn State, and we'll love to collaborate and work with them. With that, Kai, I'll pass it on to you, and thank you very much for taking out the time to talk to us.
Thank you, Dr. Priya. Thank you, everyone. Firstly, I would like to thanks for this opportunity to share my knowledge about this field, and also my topic is the Halide Perovskite crystal and applied physics for the photovoltaic application. So, so this outline will include the introduction part, which I will describe shortly about the background and the overview of this field, and also the thrust why we use the halide perovskite material. And secondly, I will share my knowledge about the crystal of this perovskite and our recent work on the promotion of this multi-crystalline perovskite film, meanwhile this monocrystalline perovskite film, and their device efficiency, lifetime, which are the very limiting factors for their commercialization. Finally, is the summary and outlook. So, so the photovoltaic is a technology that can convert the solar energy into the electricity. And the solar energy we receive on the Earth can be quantified with this number, the AMS 1.5, that describe how much energy from the solar we can receive on the ground of the Earth. So this number would be 100 million watts centimeter per square. And nowadays, the state-of-the-art efficiency of the photovoltaic, like the single junction monocrystalline silicon solar cell, they can reach 26.1% efficiency. That is the highest efficiency of the photovoltaic currently commercial. So that will provide us like 201 watts meter square, this power harvested by the photovoltaics. And so let's imagine if the Earth is covered by all those photovoltaic cells and panels, then we can get very large number of the power that harvest the energy. But let's consider the global energy consumption in a year. So that will be like 550 quadrillion BTU, that corresponding to this 1.6 times 10 over 14 magnitude kilowatt hour, this energy. So that means shining the sun on the, and we can roughly will need 2.5 hours working time for the photovoltaic. Then we can harvest all the energy that consumed by a whole year globally. So that, of course, this imagine is not real, but this at least gives us possible solution to use the solar energy and how much energy we can harvest from the solar cell and photovoltaics. That probably a promising way in the future to replace all those unrenewable energy sources we currently are using, like petroleum, charcoal, and so on and so forth. So for the market, the photovoltaic still have very low market share, less than 1% globally. And taking US as an example, but this photovoltaic market is growing very fast, exponentially growing. So for example, in 10 years ago, the energy supply is around 2.5 gigawatts from the photovoltaic, but nowadays it's like 70 gigawatts energy. So that consists compromise, like that consists 2.6% of the US electricity. And now the photovoltaic is entering the grid, and a lot of people are installing these photovoltaics. But the current photovoltaics mainly dominated by the silicon photovoltaic technology. They include monocrystalline, multicrystalline, and thin film silicons, and they can and a lot of the manufacturers coming from China, and so that a lot of this energy is exported from countries outside the U.S. And so that the U.S. CETO, this Solar Energy Technology Office, they release a lot of opportunities to pursue even more aggressively to lower power price. So the goal of the sunshot in 2030 is like 3 cents per kilowatts hour. So that would be so to lower this solar electricity cost, multiple factors need to be considered, like the durability, which means the lifetime and life cycle of the product, and also the efficiency. If we can improve the efficiency, then the power we can harvest per price will be larger. And meanwhile, the manufacturing and the installation, maintenance, all those factors need to be taken into consideration. And those with all these stimulations, the society is still searching for some candidates, material and devices, so that this material and device will drive us to a new area with lower electricity cost by the photovoltaics. So recently, the perovskite material is a very promising candidate because the efficiency, you can see from this efficiency figure, the efficiency jumps very fast in recent several years. Nowadays, for perovskite solar cells, they can reach 25% efficiency, and this is much higher than the multicrystalline of the silicon solar cell, and even approaching the limit of this single crystalline silicon solar cell. But we needed to know that silicon solar cells still have needed to be manufactured with a lot of critical requirements. But this perovskite is very easy to synthesize. They can be grown from the solution and spin coating, and finally we can get very high promising efficiencies. And all of this high efficiency comes from the materials merits. The material have a lot of advantages intrinsically. For example, it has direct band gap, and so that very thin film, like 700 nanometer, this layer, perovskite layer, can harvest 90% of the light. And also the band gap of this material can be tuned to near infrared region. So the visible and the near infrared region covers like 80% of the solar energy. And also the material have a lot of optical electronic properties, which enable them to have very small effective mass of electron holes and large electron hole diffusion lengths, so that energy loss during the operation of the perovskite solar cell will be minimized. So with all of this promising property of this material, the efficiency is driving very high, and a lot of researchers are developing new methods and new technologies to make highly efficient perovskite solar cell. And the name of the perovskite can have very long history, and a lot of oxide-based perovskite have been widely used in piezo and some other field. And here's just a short note for the name of the perovskite. So in terms of the working principle of the solar cell, so here basically I will show very quick review of the working principle. So the perovskite material is the light absorption layer. It's inserted between the Hall transfer and the electron transfer layer, and at the very outside there are electrode. So those electrodes will collect the electron and the holes, which is created in this perovskite layer. So when the light comes into this perovskite material, then the light will be absorbed by this material. So during the absorption, the electron will be excited from the lower energy level from the perovskite to the higher energy level. The higher because the perovskite is the semiconductor, so we name this band like this high energy level. We call it a conduction band, and then correspondingly there's valence band. So electron and holes will be created at the bottom of the conduction band and the top of the valence band, respectively. So when we insert this hole and electron transfer layer and the electrode correspondingly, then this device will automatically have an internal building potential, and this building potential will drive the electron and holes towards the cathode and anode correspondingly. So that is the major working principle for the perovskite solar cell. The perovskite harvests the electron and holes, and electron holes are driven through all those collection layer and be collected by the electrode correspondingly. And because the perovskite have those properties, like it is needed to absorb the light, so that band gap is critical, because band gap is corresponding to the wavelength of the light which it can absorb, and also the transport property of this material. If the mobility of this electron holes is low, then there will be a lot of energy losses within this layer, so that the final number of the electron holes collected at the electrode will be very small. That is not the case we want. And then you will see this device structure. So this is corresponding to this device structure, and we use this device to harvest the light. So so it is very important to make this perovskite layer with high quality. High quality, I mean the crystal needed to be very good form, so that this layer, at first, this layer need to be homogeneous, and also the crystal have very small grain boundary, so that electron and hole losses will be minimized. And also in the system level, we needed to deal with all those layers to make the layer and the film quality good to integrated with each other. So electron and hole transport and also the photovoltaic process is ensured in a high efficiency. And nowadays, people have developed a lot of device structures to maximize the efficiency. And this picture shows the perovskite solar cell, which now can be manufactured in a larger area and prepared to enter the market. And so the next part, I will introduce the perovskite crystal and our work on the multicrystalline perovskite thin film and monocrystalline perovskite. So fundamentally, this perovskite has this crystal structure. It belongs to this space group, PM3M. And normally we use the tetragonal or cubic face of this crystal. because they are in this form at room temperature. And the crystal is very important because it determines the electronic band structure of this material. And the electronic band structure will related to the band gap, firstly, and also the effective masses and the mobility of electron and holes. So the band gap is corresponding to the light absorption. So it corresponding to what wavelengths of light can be absorbed. So if we wanted to use to maximize the utilization of the sunlight, then we need to shrink the band gap so that the material can absorb as much as light from the sun. And the mobility corresponding to the charge transport property. So if we wanted to if we wanted to increase the efficiency, we needed to optimize the transport. A good transport will ensure a good charge carrier collection at the electrode. So that means there will be less electron and hole losses during the transport process. So this perovskite crystal property will be very important to make a high efficient device. And so far there have been developed a lot of techniques to manufacture and processing this perovskite thin film, and this can be spin coating. So because perovskite can be the manufacturing of perovskite is usually based on a solution processing. We firstly dissolve the precursors in a solution, so that solution can be spin coated or be slow die coated and blade coated. So these three are currently the major processing method to make the thin film of the perovskite crystal. And people also use this vacuum evaporation to evaporate the precursors so that this crystal can be synthesized in this way. But considering the cost and the easier of this manufacturing, then these three methods are still dominate this the current research of the perovskite solar cell. Because of this solution processing method, the crystal property and the film quality of the perovskite layer is have a lot of issues. The one biggest issue is the grain boundary. And people are trying hard to minimize the grain boundary and to make the film with larger grain size and a smaller density of grain boundary. And the reason is that because grain boundary is harmful for the charge transport, and they will introduce a lot of shallow traps in the at the grain boundary. Then these traps will have several mechanisms to consume this electron and holes. It can be the charge carrier can be scattered and can be captured by this traps at the grain boundary, and also and in this manner the device will have poor performance because all those photo carriers are lost during the transport. Another problem of the perovskite is the defect density. So there will be a lot of vacancies and lattice defects within the crystals. That is because the material itself may the bonding between the atoms is not so strong. And for example, the methyl ammonium, that atom have some is bonding with the sublattice with ionic interaction. So that is not strong compared to the typical covalent interaction in those oxide perovskite. So in this way, there are a lot of traps created automatically in these crystal lattice. We need to overcome this problem and also overcome this grain boundary issue. So considering these two problems, there are a lot of disordered state. in terms of the band structure. So for example, the vacancies in the letters, like the at this any side, there were so that this lot of subband and deep defect will be created within the band gap, and those unwanted electronic states will have a lot of issues to, for example, to recombine, to induce a recombination of electron and holes, and then to induce the trap-assisted recombination. And all of this recombination loss of electron and holes is the major loss mechanism for the efficiency of the perovskite solar cell. So these two problems we needed to address. And then we have developed several methods from very atomic scale and nanometer scale to the meso scale, and even at the device scale to compromise those issues and to promote a higher quality and high performance devices. For example, we developed a very promising ink for crystallized perovskite with lower energy consumption. For example, typical method to crystallize the perovskite, people use this ionic ink, which is widely used and dominated by all the research groups. This method containing the solvent like DMF, and this DMF can dissolve the precursors of the methylammonium iodide and the lead iodide. And these two precursors are the components that consist the perovskite structure. So in this typical solution system, those precursors are ionized into free mobile ions like this ammonium ion and the lead ion, and also these iodine ions. So they are freely movable and very disordered. So during the crystallization, firstly the solvent needed to evaporate. Then these disordered ions needed to be assembled with each other to form these highly ordered crystals. So that process is very require a lot of additional requirements, like it needed to be very high temperature, like 100 to 150 degrees C to evaporate the solvent. The DMF is very high boiling point solvent, have a BP around 150. So that the temperature is required. And also the process is very slow, and because all these ions needed to be rotated and assembled in a good manner to form this crystal. But this process will consume additional energy for their rotation and assembling. And meanwhile, in the researches, people using a lot of additional processings. For example, they use an anti-solvent. The anti-solvent is to drain out this DMF so that it will promote the super saturation to foster the crystallization. So so overall, the typical method using this non-ionic solvent system have a lot of these problems. And in this manner, we developed a new precursor ink system. We use ammonium assisted method to liquefy the crystal and to maintain the intermediate state cluster, so that this intermediate state have a certain level of order of the crystal structure, but it can be spin coated and solution processed because it's a liquid. And in this way, we will have less energy to consume and have less effort to consume to make a good crystal. So starting from the fundamental, because the crystallization can see from this diagram, phase diagram, then there are multiple ways to assist the crystallization. And then usually for the solution processing and spin coating ways, we use this concentrating method. So the initial state is the unstable state, which contains is a stable state with an unsaturated zone, and in this zone, the solute of the system is not saturated, so that they can be contained, they can be maintained in the solution state. But when we evaporate the solvent, then the solute concentration will be increases, and like showing in this yellow arrow, and this will lead to this metastable zone. And this metastable zone is responsible for the crystallization and initiate the nucleation and further the crystal growth. So we need to keep this system in this green zone so that this crystal will be in a good way. And typical ink, the reaction can be seen here. By removing the DMF, by adding the DMF, they are ionized in the system. And by further removing them, these ions will be further assembled together to form the crystal. So that is but this removing of this DMF solvent require very high temperature, and so this is the current status of the research. But we developed this new ink, and we use a low vaporing solvent like the acetonitrile, and has a lower BP temperature, and also this we find this there is an intermediate state, this cluster, which can foster a greater, better film quality and crystal. So this intermediate cluster is soluble in this low acetonitrile solvent, and by removing this, we can get the crystal without any annealing process. So to verify this intermediate state and to make it different from the conventional ionic ink, then we do this characterization, and we find that by charging this solution, because in the ionic solution, then these ions in this ink will have the redox reaction, so that we can see here, there will be a lot of precipitations of iodine and lead. So that means there are some reactions happens, and this is evidence showing that there are a lot of mobile ions of iodine and lead inside of this typical ink. While in our ink, we find that there's no precipitations. So that means those ions is not existed in this form in this solution. And also we check the ionic current, and their magnitude lower ionic current, and means the ion concentration in the non-ionic ink is really small. So that verify our assumption that we made this intermediate state, which is not ionic. And then we propose these reactions, this chemical reaction. So basically, during the solution preparing process, the perovskite precursors and this molecular additive are added together, and we add this acetonitrile as a solvent. So finally,